In the last video we learned about the probability density function, which incorporates information about the distribution of a random variable, or in other words, how likely different ranges are across the values that this random variable can take for a continuous random variable. But you might ask the question, how does one find such a probability density function? For example, this one for the centimeters of rain looks a little bit crazy, and it's kind of doubtful that you'd be able to just draw this for any quantity that you're interested in. Now, one option that hopefully you'll have a lot of the time is to use historical data. And with this you can develop a histogram that gives a great approximation of a probability density function. In other cases, there are some special families of distributions that arise quite often for modeling purposes or in practice. And we'll take a look at two of those today. We'll first talk about the uniform distribution. And let me give an example. Suppose that you have a company that's manufacturing industrial pipes which vary in length from 9.9 meters to 10.1 meters. And suppose that you think that all the values of pipe lengths in this range are believed to be equally likely because of the way that your machinery works. So this equally likely idea is important. This is what characterizes a uniform distribution. So here's the probability density function, the PDF, for this uniform random variable that captures the length of a random pipe that you choose from your product line. Now, notice that this is entirely flat, which reflects the idea that all of the ranges of equal length have equal probability. The area under the curve here is equal to 1, and you can actually calculate it in this case because it's just a rectangle. So we have 5 times the difference between 10.1, which is the top end of the range, and 9.9, the bottom end of the range. This is 5 times 0.2 is equal to 1. Now you can ask a couple of questions here. So the first question could be, what's the probability that the pipe length is, say, 10.02 meters? Hopefully you said 0. Remember, for a continuous random variable, any single value has a probability of 0. But what if I'd like to know the probability that the pipe length now is in a range, specifically between 9.9 meters and 10.05 meters? And to do this, let's write it out and see what we get. So I've duplicated the drawing of the probability density function here. Not quite as nice as the one on screen, but it'll do just fine for us today. Now, the value that we're interested in, the top end of the range, lies right here. It's 10.05 meters. And I'd like to know the probability that the random variable lies within this range between 9.9 and 10.05. So let's write this out. Probability that 9.90 is less than or equal to x, where x here is the length of a randomly chosen pipe, and 10.05. And I can do a calculation for this area, again, because we're just looking at a rectangle. This is just the height, 5, times the difference between 10.05 and 9.90, which is equal to 5 times 0.15, or 0.75. So 3 out of 4, or 3/4 of the time, the pipe lengths will lie within the range 9.9 to 10.05. We'll move on to another distribution now, the normal distribution. Now this, perhaps you've heard of it before, this is an extremely common distribution, perhaps the most common continuous random variable that you'll see. It arises a lot in practice. It's particularly whenever your randomness is composed of a bunch of different independent additive components. For example, if you have maybe a ton of customers who come to your store every week and you think you can approximate it with a normal distribution, this is reasonable because every customer maybe behaves a little bit independently. And so it turns out whenever this type of thing happens across tons of different disciplines, you end up getting this shape of a normal distribution. Notice that in here, as opposed to the uniform distribution, the probability distribution across the different values is not equal. It peaks at the expected value, which in this case on this picture is 10, and then decays or drops off as values get farther from the expectation. Now the expectation doesn't have to be 10, you could shift this curve wherever you'd like. And there also is another parameter for the variance, which you remember we talked about in the last video. For example, you might have a random variable with the same expectation, 10, And it may still be a normal random variable, but it may have a higher variance here. And so you see that the spread is much wider than in the first case. Now, normal random variables are useful, especially if we can use them to calculate probabilities. And to do this, we'll need the concept that we'll discuss in the next video, and that's a cumulative distribution function.